This is the mind map for metals, for the metals chapter. Okay, so we start off with looking at pure metals. Now, pure metals have very few application. Okay, we don't really use pure metal in our daily life because they are very soft and they corrode easily. Corrode easily means that they react with air and water to form oxide. Okay, that is the meaning of corrode easily. Corrode easily means that the metal react with air and water to form oxide. Now, why are pure metals very soft? This is actually the structure of pure metal. So from here we can see that the structure of pure metal, the atoms are of the same size and packed tightly in layers. Okay, they are all in layers, and it is because of the fact that they are all in layers, when you apply a force to the pure metals, all the atoms, okay, the layers of atoms will slide over each other. Okay, because they are all nicely in layers, so when you apply a force, then the layers of atom will slide over each other, and then they will be out of shape. Okay, and because of that, they are soft. Also, the property, another property of pure metal would be they are ductile. Ductile means the pure metal can be made into wire form. They are malleable, can be made into sheets. So all these are the terms which you have to remember the definition. So ductile means can be made into wire, malleable means can be made into sheets, into like a piece of paper. Now, because the layers of atom can slide over each other, so this is the part about why pure metals are soft. Okay, why pure metals are soft, so you have to explain this part. Atoms are of the same size and packed tightly in layers, and because of that, layers of atom can slide over each other when a force is applied. And because of the fact that they are all packed very tightly together, pure metal have high density, because density is mass per unit volume. So if they are very packed like this, means that for a unit of volume, the mass would be very high, so they have high density. Now, another property of metal is that they can conduct electricity and heat. Now, this part deserves more attention. Now, why do pure metals conduct electricity? Okay, why do pure metals, or why do metals conduct electricity? So this is the explanation here. So for example, take the example of lithium atom, of lithium. Lithium is a group 1 metal. Now, when in the lithium atom, in the lithium metal, atoms are packed very tightly together like this. And this red cross here are the valence electron. Lithium has 3 electrons. So first shell can accommodate 2 electrons, second shell 1 electron. So second shell would be the valence shell. Okay, so lithium 3 electrons. So the second shell would be the valence shell, which has 1 valence electron. Now all these are the valence electron of the lithium atoms. Now this particular valence electron is attracted by the proton here. Because proton is positively charged, electron is negatively charged, so they will be attracted. And because they are so packedly tight with one another, this valence electron is also very close to this nucleus, to the proton inside this nucleus. Therefore, this valence electron is also attracted by this nucleus. And likewise, this valence electron is also attracted by this nucleus. This valence electron is also attracted by this nucleus. So all the valence electrons are attracted in all directions by all the nucleuses surrounding it. And because of this strong attraction, this valence electron eventually will break away from the respective atoms. So all these valence electrons will break away from the respective atoms and become delocalized. So all these valence electrons now do not belong to any one of the lithium atom. they become delocalized, meaning that they are moving freely. So when the valence electron of lithium break away from the lithium atom will become positively charged. Because you lose one electron, so it will become positively charged. So eventually for metal, it will consist of positively charged metal ions surrounded by sea of delocalized electron. So all these are called delocalized electrons or mobile electrons. So this is actually the structure for metals, for pure metals. Okay, another diagram to represent that would be like that. Okay, all these are positive metal ions, and all these blue dots here are actually the delocalized electrons, sea of delocalized electron, metal cations or metal ions is positively charged. So over here is the explanation. Over here basically is the explanation on why do metals conduct electricity. Due to the tightly packed atoms, outermost electrons or the valence electrons of metal atoms can break away easily from atoms. So when the valence electron break away from the atoms, the result would be positive metal ions surrounded by sea of mobile electrons. So the result would be like this when the valence electron break away from the atoms. And the mobile electrons can carry charges and transfer electricity and heat. Okay, actually transfer electricity and heat, not only heat. So this part basically is the explanation for why do metals conduct electricity or why do metals conduct heat. It is all because of the delocalized electrons or mobile electrons that are free to move around and transfer the electric charges and also to transfer the heat. Very important, this part. Now we go to this part here, pure metals. So the atoms are in pure metals, the atoms are held by strong metallic bond. So metallic bond actually is the attraction between positive metal ions and sea of delocalized electron. So this part is a follow-up of here. So I repeat, metallic bond is actually the attraction force between positive metal ions and sea of delocalized electron. Because the positive metal ions and the electrons, they are oppositely charged, so they do attract each other, and when they attract each other, the bond is called the metallic bond. Okay, metallic bond, high boiling point and high melting point. Because the positive and the negative charges, the attraction between the positive metal ions and the electrons are quite strong. Therefore, the boiling point and the melting point for metals are quite high. Now let's look at alloy. Now what is actually an alloy? Alloy basically is a mixture of a metal and a non-metal, or a metal and a metal. That is an alloy. It could be more than one metal or it could be more than one non-metal. So this is the structure for alloy. Structure, atoms of different elements are of different sizes. So in order to describe this structure, this would be the description. So atoms of different elements are of different sizes, and because they are in different sizes, it makes the arrangement of atoms irregular. So what happened is the arrangement of atoms is irregular, and because the arrangement of atoms is irregular, layers of atoms cannot slide over each other. That is why alloy is hard and strong. When you apply a force to the alloy, the atoms cannot slide over each other. It is because of this reason. So this part actually explains why alloy is hard and strong. Properties and applications. So alloy can be used in many applications. First of all, it can be used to improve appearance. For example, for certain keychain, and the alloy user to make the keychain is called pewter. This kind of keychain is quite shiny and is quite expensive, so the alloy is called pewter. And also alloy is used because it is resistant to corrosion. For example, stainless steel, because stainless steel cannot rust. It is used to lower the melting point of metals. An example of alloy used in this application is called solder, and solder is used to join the metals together. So this part basically tell you the composition of each type of alloy. Brass is copper and zinc, solder is tin and lead, pewter is tin, copper and antimony. All these are metals. Stainless steel is iron, carbon, nickel and chromium. This is chromium. Steel is carbon and iron. Bronze is copper and tin. Now you need to remember the composition for bronze, steel, stainless steel and brass. Solder and pewter basically you don't need. So this part, it's about alloy. Now let's go into the reactivity series. Now these are the common metals that we'll be studying, and all these metals have different reactivity level. Some metal is more reactive, some is not. So this is a reactivity series whereby the higher the metal is, the more reactive it is. Reactivity series, the higher it is, the more reactive. The lower it is, the less reactive. So there is a way to remember this sequence. So you have to remember this sequence, exact sequence. Okay, so P is potassium, so it's actually start with P here. Na, sodium, start with S. Iron, I, start with I. Lead, start with L. So okay, you can use acronyms to remember this. So the acronyms that I use, that I've seen would be please, sand, cat, monkey and zebra in large heavy cage soon. Ag is silver, start with S, so it's soon. So I repeat, please, sand, cat, monkey and zebra in large heavy cage soon. Okay, so you need to know which are the metal that react with water, which are the metal that react with steam, and which are the metal that react with steam, as well as which are the metal that react with hydrochloric acid. So for example, for cold water basically only the top 3 metals react with cold water, the rest don't react. Steam basically is up until iron. Anything below iron do not react with steam. Steam is H2O gas. Now it's the same for hydrochloric acid. All the metals react with hydrochloric acid up to iron, and everything below iron do not react with hydrochloric acid. So hydrochloric acid and steam, the cutoff is the same. The last element that react with steam and hydrochloric acid would be iron. Anything below iron do not react. For cold water would be the top 3 react, the rest do not react. For magnesium actually do react very slowly with cold water, but for O level wise, magnesium, we say that it does not react with cold water because it is so slow. So for magnesium it is no. And of course aluminium is in between magnesium and zinc, and both of these metals do not react with cold water, therefore aluminium also do not react with cold water. Aluminium does react with steam because magnesium and zinc do react with steam, and aluminium does react with hydrochloric acid because both of these do react with hydrochloric acid. Now when potassium reacts with cold water, when we put a piece of potassium in cold water, the reaction is very violent. RXN stands for reaction. It is very violent. Hydrogen is produced and it would burn with lilac flame. Lilac means purplish, purple color. Sodium, the reaction is less violent, therefore the color of the flame is yellow. And then for zinc oxide is very cute, because zinc oxide, it is yellow when hot, white when cold. The other oxides usually they only have a fixed color, but for zinc it is different when it is hot and cold. Now take note that for example, below silver will be Au. Au stands for gold. So gold also don't react with water, steam and HCl. Now on the right hand side here, okay, so reactivity series you have to remember. Now for the right hand side here, we have different reactions. Now if the metal does react with water, you get hydroxide and hydrogen. An example, potassium and water, you get potassium hydroxide and hydrogen. Metal and steam, you get metal oxide and hydrogen. Metal and acid, you get salt and hydrogen. So all these three reactions you have to remember, and all these three reactions, hydrogen will be given off. Now let's look at the page 2 of the mind map. Now the page 2 of the mind map concerns with the reaction of metal compounds, because most of the metal found in nature, they have already combined with another substance. Okay, an example would be oxygen. Okay, an example is copper oxide. So copper is very useful, but copper oxide is not useful. But in nature, most of the copper is found in this form, copper oxide. So we have to think of a way to split copper and oxygen. And one of the way to split copper and oxygen is by burning copper oxide with carbon. Okay, we heat them, we mix copper oxide and carbon, we heat them, and when copper oxide is heated with carbon, the oxygen and the copper will be splitted, so you get copper alone, and the oxygen here will combine with carbon to form carbon dioxide. So copper oxide plus carbon, you get copper and carbon dioxide. Now not all the metal oxide can be reduced in this way. By the way, this is a reduction reaction, because there is a removal of oxygen from CuO to Cu. Oxygen is removed. When there is a loss of oxygen, it is a reduction process. So we say CuO is reduced to Cu. Now not all the metal oxide can be reduced using this way. For example, potassium oxide, K2O. Potassium oxide is K2O. When we heat it with carbon, you don't get anything. There is no reaction. Why? Because your potassium oxide is K2O. When we heat it with carbon, there will be no reaction. Why? Because this potassium is very reactive. This potassium is very reactive, and when the potassium is very reactive, it will hold on to the oxygen very strongly, and this carbon cannot split them up. So all this oxide, all this metal oxide up to magnesium oxide cannot be reduced using this way, using heating with carbon. Only this can be reduced. And for silver oxide, because silver is so unreactive, silver oxide is like this. Silver oxide, you don't even need to heat it with carbon. You can just heat the silver oxide by itself, and then you get silver. Okay, oxide is reduced by heating. You just need to heat it, and then you get the silver. Because silver is so unreactive, so it's so easy to split the silver from the silver oxide.